This is the lecture notes for section 5.2 on probability rules. By the end of the section, we should be learning about how to describe chance behavior with probability model, how to define and apply the basic rules of probability, and to determine probabilities from a two-way table, and being able to use Venn diagrams and be able to determine probabilities based on those diagrams. Um, in the earlier section, we learned that probability was along as a proportion of the time a particular event happens over a long series of, of random events. And we use simulation to do that chance behavior. Says, fortunately, we don't always have to rely on simulations. We can look at a set of rules that define how probabilities work. Probabilities work by dealing with two things. One, a list of all the possible outcomes of that random occurrence. We call it the sample space, and we give it the letter S. And what is the probability or that long-term proportion for each of those outcomes? The probability model describes what are the things in the sample space and what is the probability of each of those outcomes. For example, if we roll two dice, one green, one red, then we can say what is the sample space for that. You can see it consists of 36 different outcomes from 1, 1. The red die and the red die and the green die are both being green or being one, all the way to 6, 6, 36 different outcomes. And if they're fair dice, that means that each of those outcomes are equally likely. Another sample space could involve flipping a coin, in this case, three times. Um, if we flip a coin three times, there are eight possible outcomes. I can enumerate them from I got all tails to I got two tails and a head. And there's actually three different ways that you can get two tails and a head. I can get one head, sorry, two heads and a tail, and there's three different ways that that can happen, and then I can get all heads. Since each of these eight outcomes are equally likely, we say that each of them has a probability of 1/8. We have a probability model. Hey, here's all the possible outcomes. Here's the entire sample space, and each of those things in the sample space happen with probability 1/2. A group of outcomes is called an event. So it says an event is a collection of outcomes of some chance process. We typically use capital letters like A, B, C to name these outcomes. So if an event is A, we say the probability of that event is P of A. In the dice rolling example, suppose we define the event as as the sum of the two dice are 5. There are how many different outcomes with a sum of 5? Well, we've got the 4 and the 1, the 2 and the 3, sorry, the 3 and the 2 and the 3, and the 1 and the 4. There are four possible outcomes where the result is 5. And each of those outcomes, because they're all equally likely, uh, has a probability of 1/36. So how many different ways can we write this? Well, the probability event A, which is the probability the sum is 5, therefore is 4/36. Suppose event B is defined as the sum is not 5. Then um, we could say that the probability B, or the probability the sum is not 5, um, could be thought of, or all the things that are all the outcomes except for these four. Um, Maybe we could think of that as one, all the outcomes minus the probability that the sum is not 5, making this probability as 1 minus 34/36, which leaves us 32/36. And if we're really, really keen, I suppose we could reduce that to 8/9. Um, we notice that probability of A plus the probability of B, that is the probability the sum is 5 plus the probability the sum is not 5 uh, is 4/36 plus 32/36 or 36/36, which is equal to 1, because those two events combine to make the entire sample space. Let's consider event C, so call that the sum of 6. If I go back, the sum of 6 has these possible outcomes. There seems to be 5 of them. So the probability of C, which is the probability, again, the sum is 6, would be 5/36. What's the probability of getting a 5 or a 6? If the sum is 5 or the sum is 6. That is, what is the probability sum is 5 or sum is 6? Since they have no probability or no events in common, we can simply say that the probability of A or C, again, the probability the sum is 5 or the sum is 6, is the probability that the sum is 5 plus the probability the sum is 6, or it is the probability of A plus the probability of C. In that case, some probability the sum is 5 is 4/36. Probability that the sum is 6 is 5/36 for a total of 9/36. Going on to the next page. We have some basic rules of probability. We know that already that a probability is some number between 0 and 1. The probability of all possible events together has to have a sum of 1. If the events in the sample space are equally likely, sorry, the outcomes are equally likely, then we can think of the probability of event A as the number of outcomes that correspond to event A divided by the total number of outcomes in the sample space, like we did in the dice example. The probability that an event does not occur is 1 minus the probability that the event does occur. We saw that in that last example. And if two events have no events or outcomes in common, then we can simply add up the two probabilities together. By the way, this idea that two events have no events in common, it has a special name. We call those events mutually exclusive. We also use the word disjoint to describe those two events. Because mathematicians are lazy, we have a tendency to take all those ideas that we just talked about and write them in more cryptic symbols. For example, probability of A is some number between 0 and 1. The probability of the sample space is 1, so list of all possible events. For the idea of the event A not happening, we use a superscript C. We read A superscript C as event not A not happening. And as I said before, it can be found by taking 1 minus the event, the probability the event does happen. And again, if two events are mutually exclusive, then the probability of A or B happening is the probability of A plus the probability of B. Let's try these out with some examples. It says, listen, distance learning courses are rapidly gaining That shouldn't be population. It's probably should be popularity. Popularity among college students. Randomly select an undergraduate student who's taking a distance learning course for credit and record the student's age. Here's the probability model. Here's the list of all the outcomes and the probabilities associated with each of them. Is it a legitimate probability model? Well, the probability of the sample space would be the sum of each of these probabilities. 7 plus 7 is 14, plus another 4 is 18, plus another 2 is 20. Carry the 2. 2 plus 5 is 7, 8, 9, 10. So indeed, we found out that this sample set probability is 1, just like it should be. So find the probability that a chosen student is not in the traditional age group. Well, I could write that as the probability that the student is 24 to 29 or 30 to 39 or 40 and over. And I could add up all those probabilities. 0.17 plus 0.14 plus 0.12. 7 plus 4 is 11, plus 2 is 13. Carry the 1. 1, 2, 3, 4. Looks like it's about 43%. That's one way to do it. Another way to do it is to recognize that being not in the traditional group, being not 18 to 23, can be thought of as 1 minus the probability of being in the age group 18 to 23, which would be 1 minus 0.57, which ends up being 0.43 as well. You can decide for yourself which one of those is easier to do. Here's another little check for understanding. It says choose an American adult at random to find these two events. A, person has a cholesterol level of 240 milligrams per deciliter or above. We call that having high cholesterol. Event B, the person has a cholesterol level of 200 to 239 milligrams per deciliter, and we call that event the borderline high cholesterol. Explain why events A and events B are mutually exclusive. A and B are mutually exclusive because event A and event B can't happen at the same time. Okay, someone can't have high cholesterol and borderline high cholesterol at the same time. Those two groups are non-overlapping. It says, say in plain language what event A or B means. Um, uh, A or B means the person has either high cholesterol, and I'll just use abbreviation CO2, or borderline high cholesterol. What is the probability of A or B? Well, again, because these are mutually exclusive events, this is equal to the probability of event A plus the probability of event B, which in this case is 0.16 plus 0.29. If we add those up, 6 plus 9 is 5, carry the 1. That looks like about 40, 45%. right? Um, if event C is someone has normal cholesterol below 200, what is the probability of C? Well, we could say that the probability of C is 1 minus the probability of A or B, which is 1 minus 0.45. So it looks like about 55% have normal cholesterol. All right, going on to the next page. We can often look at events in the form of a two-way table. We talked about two-way tables way back in chapter 1. Um, college students at a college statistics class wanted to find out how common is it for young adults to have their ears pierced. They recorded data on two variables, gender and whether they had a pierced ear for all 178 people in the class. Here's a two-way table for the data. Um, Suppose we choose a person from the class at random, find the probability that that student has pierced ears. Well, the probability of having pierced ears with this data set, well, how many have pierced ears? Well, if we go to pierced ears, yes, that would be 103 out of the 178 in the class. And we're just going to leave that number as a fraction. How about is a male with pierced ears? Well, we could think of that as the probability of being male and having pierced ears. And that probability, how many males are there with pierced ears? That probability is 19 out of the 178. Now here's the tricky one. What about the probability of being a male or having pierced ears? Now we're going to use the inclusive or here, which means it means male or pierced ears or both. And in this case, how many males are there with pierced ears? There's 19. How many males are there without pierced ears? There's 71. And then how many females are there with pierced ears? There's 84. And that's out of the 178 in class. If I add that up, 9 plus 1 is 10, plus 4 is 14. Carry the 1, 1, 2, 2 plus 7 is 9, plus another 8 is 174 out of 178. We may have been able to recognize also that that number is simply all of the numbers in here, these four, with the exception of the four that are females without pierced ears. So maybe we could have also thought of this as 1 minus the 4 over 178. All right. Note in the previous example that we can't use the addition rule. Why? Well, because being male and having pierced ears is not a mutually exclusive event. They have something in common. In fact, if they were mutually exclusive, then the probability of them both happening at the same time would be 0, but it wasn't. It was 19 out of 178. So what's going on here? Well, if we picture the sample space as a Venn diagram, we have essentially four different regions in which we could have these things. If we call event A having pierced, being male, and event B as having pierced ears, there's this overlap, and that's where they're both A and B happening at the same time, and those are the males with pierced ears. There's also this area outside the two circles. These are the people who are not male and not pierced. So that's the group with four people. Probability of this group, probability of that group, not A or and not B is that 4 178th. And please note again, we have this overlap, which means if we were to count everyone in event A, so circle here, and everyone in event B, which is this group here, this area gets counted twice. And so that leads us to our what's referred to as the general addition rule for two events. And this is a rule that's true regardless of whether you have disjoint events or not. And that rule is probability of A or B is the probability of A plus the probability of B minus the probability of A and B. If we go back to that previous example, we could have said that this is the probability of being male, which is 19 out of 178, plus the probability of male, which is 103 out of 178, plus the probability of being, let me try that one more time. Probability of male is 90 out of 178. Probability of being pierced is 130 out of 178. But we just have to subtract off the 19 that are both male and pierced. And that will also get us to the 174 out of 178. Okay, let's try this again, making a new two-way table. So the standard deck of playing cards with the jokers removed consists of 52 cards in 4 suits: clubs, diamonds, hearts, and spades. Each suit has 13 cards or denominations, ace through 10 plus jack, queen, and king. The jack, the queen, and the king are referred to as face cards. Imagine we shuffle a deck, thoroughly deal one card. Let's say event A is getting a face card. Let's say event B is getting a heart. We can make a two-way table of this. This side will have A and not A. This side will have B and not B. Let's start with just how many face cards are there? Well, there's 3 face cards and 4 suits. There are 12 face cards, so we'll put a 12 there. How many hearts are there? Well, for each suit, there's 13 cards, so we'll put a 13 there. How many hearts that are face cards exist? And the answer to that question is that there's 3: the Queen of Hearts, the King of Hearts, and the Jack of Hearts. Now, because we know there's 52 cards, we can actually start filling in all the rest of the table. Like hearts, there are 3 face cards, there are 10 non-face cards. For face cards, there are 3 face cards that are hearts, there are 9 that are not hearts. There must be, if there's 12 face cards, there must be 40 non-face cards because these two numbers should add up to 52. If there's 13 hearts, there must be 39 cards that are not hearts. And as you can see, going both this way and this way, this number must be 30. What's the probability of A and B? Well, the probability of A plus the probability of B could be thought of as the probability of A plus the probability of B minus the probability of A. Oh, I'm sorry. Got ahead of myself. I was doing probability of A or B. Probability of A and B is 3/50 seconds. Sorry about that. Okay. What is the probability of A or B? Let me try that again. Probability A or B is equal to the probability of A plus the probability of B minus the probability of A and B, which in this case is 12/50 seconds plus 13/50 seconds minus 3/50 seconds. So that's 25 minus 3, which is 22/50 seconds. Now, we could do it that way. We could also have added up the 3 numbers that make up A or B or both. And you can see there that it also ends up being 52 50 seconds. Now, why couldn't we just do A plus B? Well, A plus probability of A plus probability of B, probability of B, um, ends up being 15 or 12 plus 13 out of 52. But again, we double counted the overlap between the two groups. We double counted that 3. So that's the reason why they don't add up properly. Um, if you want to look at Venn diagrams and think that makes more sense, please note that the complement of a set, here's if this is A, everything that's not inside that circle is not A or A complement. Two events are mutually exclusive if there's no overlap, like there is there, no overlap. We call the intersection of events. This is the symbol for intersection. Sorry, this is not well formatted. Intersection, by the way, the word intersection sounds like it has an N in it, and that symbol kind of looks like an N, and that's the overlap between the two groups. This symbol is union, and we use the symbol union to mean the idea of or. In the same way that intersection means the same thing as an and it means one group, one set, the other set, or the overlap. If we were to go back in time and think about the pierced ears example, we might have said, hey, here's event A, which was how many people were males with pierced ears. And that was, sorry, um, we're going to do this in the groups. Let's see if we can, let me see if I can recreate. Here's A, not A for the males. Here's B and not B for the, oh, sorry, got it backwards. A complement with 1984, and here's B and B complement with 71 and 4. If this is event B, we can think of this space here as being an event B, but not being an event A. That's the 84 non-males that are pierced. This number is where the overlap is. The 19 that were male and pierced. This one here is the 71. Those are the males who aren't pierced. And over in this section is 4 for the non-males that are not pierced. So just know that the 4 numbers in the two-way table all belong to one of the 4 distinct areas in the Venn diagram. And so we have those 4 distinct regions, and one of the distinct regions is A and not B. Those are, again, the males with not pierced ears, or the not or A complement intersection B, and that would be, again, the non-males who are have pierced ears. All right, let's try this one more time with one more set of data. All right, and in this particular case, says that according to the National Centers for Health Statistics, in December 2008, 78 of U.S. households had a traditional landline phone, 80% had cell phones, 60% had both. Let's call event A having a landline. And let's call B having cell phones. And we'll do these this time. Then diagram, we'll do it with probabilities. 78% had landlines, 7.78 there, and 60% had or say 80% had cell phones. So I'll put the cell phones right there. and 60% had both. So I'll put 60% there. Now, we know that this table has to account for 100% of everyone, meaning that this number here has got to be 22% to make up these two numbers making up 100. This number here has to have 20% so that these two numbers add up to 100. This must be 20% because these two numbers have to add up to 80. This number must be 18% because these two numbers have to add up to 78. And now we can see going either way, this has to be 2%. 2% of the households had neither a landline nor a cell phone. So making up our Venn diagram, this is me not being able to spell. This is landline. This is Vent B, cell phone. And what we could say again is these four numbers correspond to the four distinct areas in the Venn diagram. Here's the 60% that had both. Here is the 18% that were landline but not cell. Here is the 20% that were cell phone but no landline. And then out here is the 2% that were neither cell phone nor landline. It says, find the probability that a household has at least one of the two types of phones. That would be the probability of A or B, or maybe we write that as A union B. And I could think of that as 0.18 plus 0.160 plus 0.20, which ends up being 98%. What's the probability that they only have cell phones? Well, that's the probability of them being a cell phone household and not a landline. And again, we saw that in the Venn diagram, and that's 20%. Again, we got that 20% by filling in that two-way table. And we're at our summary. Covered a lot in this section, a lot of new symbols, a lot of new vocabulary, but we got it all done.